Hello, everyone. My name is Anna Kalenkova, and today I'm going to talk about methods and models in process mining. I'm working. Sorry. Um, um, I'm working at the University of Melbourne, and so yeah, let's start. Let's talk about process mining. And if you're interested in process mining, there is a nice book by Will Wander-Als that discusses algorithms in detail. And if you're interested, you can download this book and read some details, while I will give just roughly outline some algorithms, and we will discuss them. I'm also open to any questions. I'm monitoring the chat, by the way, so if you have any questions as we go, I will be very happy to answer now, so that our lecture will be really live. Yeah, so let's start, and do not hesitate to ask any questions, because I'm really looking forward to answering your questions and to provide details. So let's start very briefly with the main ideas of process mining. Process mining is a set of algorithms for the discovery and conformance checking of event logs. So we have information systems that record their behavior as event logs, and these event logs can be further analyzed. So there are mainly two types of process mining algorithms: discovery algorithms that construct process models from event logs. So here we can see information systems that records its behavior as a set of events, and then we can reconstruct the system behavior to see how this system is organized, because we do not always know, and we not always know it from the source code. Sometimes we need to rediscover and to reconstruct the system and its architecture. So let's first start with the discovery algorithms. So as I said, discovery algorithms take event logs as input. So here you can see an example of an event log. Mainly, we need only three attributes. These are case IDs. So each case corresponds to one run of the program. We have activity name, that is the name of event that happened, and we have a timestamp. So what we can do, first of all, we can filter out our table according to case ID. So now we have all the traces on all the runs of our system. And here we can see a nice example that maybe this is a kind of example from our previous life, when we have took flights, and we were living in other countries, and we were able to go somewhere to book a flight, to select a hotel, to book the hotel, and to pay. So this, at least for me, this is a kind of an example of an event log from my previous life. Yes, so now it's not possible for me to go to another country. So here we can see this event log, and suppose we have only three traces, so possible traces. So first, we register in the system, we select a flight, we book this flight, then we select a hotel, book hotel, and then we finally pay. And two more traces where, for instance, we can swap select hotel, book hotel activities, or we can perform these activities in another order. So here, just a very simple and toy example of three traces. So once again, to extract these traces from this table, we filter out according to case IDs, and then we order all the events according to their timestamps. And this is how we get these sequences of events we perform. And we consider a system where we can book a flight and book a hotel and pay and have a trip and go somewhere. So again, as I said before, I'm monitoring the chart and I'm happy to answer your questions. So let's proceed. The first and the simplest process discovery algorithm is process map, or also known as directly follow graphs. Then we analyze all these traces and we draw an arc or a line between two events if there is a sequence of if these events in one of the event log traces. So for instance, select flight, there is a trace where select flight goes after register. That means that we have to draw an arc between register and select flight and so on. So we draw all the arcs between the activities that go one after another. So that is a very simple process discovery algorithm, but although it is a simpler algorithm, it is widely used by commercial tools such as Disca. So here's an example of Disca screenshot. And if we deal with, for instance, some retail company or even banking system, it might be reasonable to construct these maps and to get some information from these maps. But if we consider more complicated software systems, that might not be always the case. Why? Let us consider this graph in detail. You see, there are a lot of loops here, from book flight to select hotel and back, and that means that actually this behavior that we see on this picture does not fully correspond to the event log, because we have here loops, so we can move around and we can replay as many activities as we want, and this does not really reflect what we see in the event log. So how to deal with this, and what models should we use if we want to be precise? If we, for instance, have an information system, software system, and we want to be precise, we want to understand the exact behavior this system produces. There is one algorithm that is called inductive miner. It is inductive because it constructs a process model inductively from this process map. So suppose we already have this process map, and we want to construct a model that is closer to our event log. So let's do that. Let's do the following. We will split this model into two parts according to one of the patterns. So here we can see, for instance, that there are two subgraphs. The first subgraph consists of only one node, register, and the second is more convoluted and complicated subgraph, and we can split our graph into two parts. Okay. Now let's move forward and let's take a look where we can also apply this split operation. So here is another split, another cut of our graph. Again, we can cut off pay, and now we have to deal with this complicated model inside. Let's also cut select. So we perform select flight, and only after that we make some activities, book flight, select hotel, and book hotel. Okay, so now let's move forward, and here we can see another card. This is a different type of card that is called parallel execution. So what does it mean? Book flight can go in parallel with select hotel, book hotel sequence, because we see that there are a lot of arrows going from one direction to another that connect these two subgraphs. That means that it seems that these two subgraphs are executed in parallel, and we make another choice. We decided not to make a sequential split, but we make a parallel split here. And the last step that we do, we make a sequential split between select hotel and book hotel. what we did, we inductively, step by step, cut our graph into parts, and then we applied this procedure again to the subgraphs. We can also represent this like a tree with a root where sequential cut is the root, and left subtree corresponds to some sub-process, and the right subtree corresponds to a sub-process. So what does this model say? It says, okay, I do register, and then I do something that is the right part of this tree. And here we say, okay, I have to do in sequence. So there is a sequence of events. First, this sub-process, this subtree, and then pay, and so on. And here we say that book flight and this subtree, this sub-process are executed in parallel. So this can also be represented as a Petrinet. So without giving formal definition of a Petrinet, I'm going to illustrate how it works. So here's our Petrinet that actually corresponds to this process tree we have discovered before. So we first make register, then select flight. Then this construction means that we execute in parallel two branches, book flight and select hotel, book hotel, and then pay synchronizes these two branches. So let us replay the first trace from our event log. Tokens in Petrinets represent control flow. So here we have token in the first place. That means that we are ready to start. And the first activity that is enabled is register. So register is enabled because it has tokens in all its input places. Here we have only one input place. Register is activated, and look, we also have register highlighted in red here in our first trace. So we start. After register fired, we now can enable the next activity, select flight. Select flight also has an input token, so it is enabled, but it produces two output tokens. Who is going to be next? Technically, here we have two transitions enabled, book flight and select hotel, because both of them have tokens in their input places. But according to our first trace, we're going to fire a book flight activity. So let's do that. Now we have only one activity, select hotel, that is enabled. Why we can't enable pay here? Because pay waits for two tokens in its input places, so it's a kind of synchronizer here. Okay, so we fire select hotel. Now please also take a look at the event log. So we move synchronously in the event log and in our Petrinet. And now the last activity is enabled. It is pay. Pay synchronizes two branches. Yes, so we reached the end here. All good. So here how the Petrinets work. So this is just a very basic, simple example. Of course, we can present more sophisticated examples and discuss them. But here, I just want to show you a very simple example that is based on this simple event log. Okay, so that was about this exact event log. But what if we have an additional trace of events? So here you can see an additional trace of events that is not represented in event log. Generally speaking, we can start selecting hotel before we select flight in our system. And this trace is not represented in the event log. That means that generally the behavior of the system allows more than we see in the event log. So how to deal with this? In 2015, we have developed an approach that allows for constructing more general process models. When we filter the event log into sublogs, then we discover process models from these sublogs, and then we merge them together. Now you can ask me, okay, but how this will help us, how we will still be able to discover this model, the more general model. Let's go to our example, and let us consider two traces: register, select flight, select hotel, and so on. This one, or we can call them cases, case 1, C1. This is how it goes, the sequence of events, and case 2. So these are the two cases, and we can analyze the events, and we can say, okay, but actually there are two regions or two sub-processes these events belong to. For instance, a register and pay events, these two events belong to two regions or two sub-processes, because it doesn't matter whether we trying to book a flight or trying to book a hotel. We always have to register, and we always have to pay at the end, at least according to this event log. So that means that these two events, they do belong to two regions. And talking about flights and hotels, here we can see two different processes, or let's call them sub-processes, because actually these two booking procedures do not depend on each other. And if we will annotate our event log in such a way that select flight and book flight belong to one sub-process, and select hotel and book hotel belong to another, then we can analyze them separately, and we can discover the models of these sub-processes independently. So yet, if we consider region 2 or sub-process 2 that corresponds to the hotel, we can construct a model that is register. It's just a sequential model of 4 events going one after another: register, then select hotel, then book hotel, then pay. And if we will consider another sub-process that corresponds to flights, we will get this green similar process: register, then select flight, then book flight, then pay. And then we can glue them together, we can merge them based on the same transitions. So here we can see the model that actually is more general. It does not only allow the behavior that we saw in the event log, but also behavior in an additional trace, because now we show that these two parts, these two sub-processes, they are executed in parallel, and they do not depend on each other. So all kinds of interleavings are now possible. And of course, this approach also allows us constructing a more compact and more structured model. So here we have an example of a real life event log of a booking system. So this is also a booking flight system, and we applied two approaches. The first algorithm constructs the model from scratch without these additional annotations for sub-processes. And here we can see a huge model that allows almost everything, and it's really hard to analyze this model and to understand what is happening there. But if we will try to extract some information about sub-processes, we can construct a more general and a more compact model from the same event log. So if, for instance, we will separate the behavior related to the forums, to the website forums where the users fill in information about so their personal information, passport information to buy the tickets, from the events corresponding to payment. We see that actually these processes can be considered independently, and in this case we will get a simpler model with a more general behavior, because now these processes do not depend on each other and can be executed in parallel. And of course we are interested how this can be applied to software systems. And if we consider software systems, we can also apply this localized logs approach. For instance, we can do it in the following way. We have two threads that are executed in parallel. And if we take event logs and apply process discovery algorithms directly, that means that we will get this spaghetti-like model. However, we would like to see how two different threads of the program communicate and how do they synchronize. For that, we can discover them separately. So first we discover thread 1, the behavior of thread 1, then the behavior of thread 2, and then we find the common line of code or the common block that synchronizes these two threads. So this activity in green, highlighted in green, waits for two incoming control flows. So it waits thread 1 to reach this point, and also it waits thread 2 to reach this point, then it synchronizes, and after it synchronizes, control flow goes simultaneously to thread 1 and thread 2. So this is a very simple synchronous communication of two threads. There also can be asynchronous communication, then one thread passes talking to another. So you can consider that as sending a message. So we have thread 1, and here we have a transition that sends message to another transition or activity of thread 2. So thread 1 is executed when then one of the activities sends, we can consider it as a signal or a token to the thread 2, and this thread waits for this token. This activity can't be executed before we have token here in this place and token in another place. And after that, when it receives the token, it proceeds. So these are the two basic ways how different threads in our software system can be synchronized. And to discover this model, we first discover thread 1, then we discover thread 2, and then also we need to discover one more complicated model, that is this model of communication between these two threads. And then we can construct such a union, such a model. So that is about discovery. So if you have any questions about discovery algorithms, I will be happy to answer. Yes?
Yes, thank you. Anna, can you hear me?
I can't hear you, sorry.
Now, 1, 2, 3. Can you hear me? Yes, perfect. So thank you for the great introduction and very basic questions. Can you please open the first slide with the table where you have case ID and action? So just the most general question is, what are expectations for the system under test? I mean, do you expect it's white box? Because you mentioned something about source code, but actually you work with black box, right?
Sorry. Yeah, so we deal only with event logs, and we do not see what's happening inside the system. The assumption here is that we do not know what's happening there, and we do not look into the code. There is no idea. So it's a kind of universal approach, and there is no idea about the architecture of the system. However, if, for instance, we annotate event logs later, as I shown with these threads, we may have some assumptions that, for instance, in event log, we have a thread identifiers, and we say, okay, that was thread number 1000 something, and we filter out and we construct the behavior of only this thread. But yes, so we can guess, but we do not have anything than this event log.
Okay, then about the table. So the column number 2 and number 3 are more or less simple, because whatever system you take, you always may define some activities, right? And you can always, more or less, always put some timestamp. Although timestamp is not clear if your system is distributed, but okay, let's have it for now, timestamp. But the first question is about case ID. Sometimes it's not really clear what's case ID. Do you have some, probably another example, how to fill this column? Because I see it's really useful, and not useful, but really important for your tools, right? To have case ID.
Yes, thank you very much for your question. It's really important to have case ID. However, much depends on the domain we use. So here is very simple domain with this booking system. One user, maybe it is one session when the user buys these tickets. In more complicated cases, this can be different. And for instance, of course, there are cases that never stop in some systems. So much depends on the domain, what we will define as the case ID, and if this case ID exists. So this is also a good question. For instance, if we're talking about banking system. Sorry, could you please?
No, let's forget about banking. I suggest to speak about social networks, Instagram or Facebook. So, for example, someone is just opening Facebook, and then you can upload image, like, share, repost, and go to next one, and it could last for like infinitely many steps. And what's case ID then?
Oh, great question. Thank you very much. That is very interesting. I was also thinking about this. So again, we can consider a session, or so it depends, of course, what we want to discover. If we are following one specific user and we want to know what do they actually do, and we can consider one long trace of one user and construct the model, how they interact with other users in social networks. And one more example, for instance, what I would also I will try to split it in day by day, for instance, hoping that, okay, based on domain knowledge and that we are all humans, I will really hope that that person will sleep sometime, and I will find these interruptions, and this is where I will identify how I will identify the cases.
Okay, thank you. And the next question is a different one. So sometimes, quite often, we have a lot of additional information, like parameters of the activities, and more. It could be some information about system context and everything else. Should you just forget about it, or do you have some tools which can use this additional information for some improving of your model?
Sorry, each time I need to turn or otherwise I hear myself, and I think, yeah, so I have some to turn off the sound. Sorry for that. Now I don't hear you, but I can speak. So it's a kind of semi-duplex, connection. I don't know. Yeah, so thank you very much for this question. You're absolutely right. From these three main attributes that are somehow essential for process mining, modern research, so already shifted to other approaches where people are interested in other attributes because they give us a lot of information, as for instance with this threads where we can identify subprocesses, and these subprocesses are identified using the fourth attribute, so that is not presented here. For instance, this can be trace number. So for instance, in one case, there can be still several traces executed. Oh, I can see questions online. Can I answer them? I would be happy to.
Surely. I would just suggest you to read the question loudly so that everyone listens, because not everyone is able to read what you see.
Oh, sure. The first question: how are optional exceptional steps in process dealt with in? So the question is about the question is about optional steps. So if I understand the question correctly, can there be some steps that we can skip because they are not important, and we want to consider only important step? That is a very steps. That is a very good question. Thank you very much. Indeed, again, it depends. It depends on the log, and of course, so there are some noise events that we do not want to see in our event log. We want to see only some essential information, indeed, that will help us to discover these models. There can be some steps that are not really important, and practically 80% of time takes for log filtering, because when we deal with initial event logs, they are not these nice tables. They can hardly be represented as these nice tables or these sequences of events. First thing we need to do, we need to clean these event logs, to remove noise, to remove these unessential steps. So that is a very good question. And here we have to make this decision, what is important and what is not, basing on the questions we have and the questions we want to answer, applying process mining methods. Oh, thank you very much. Another questions. Can we go to the next slide? What do the numbers about the errors mean? Case ID. No. Thank you very much. That is a very good question. So this is a screenshot from Disco tool. Disco is a process mining tool where you can load event logs there and you get this process maps. So what actually these numbers mean? This is number of occurrences. So that means that select flight executed 3 times after register. So this sequence of 2-step register directly followed by select flight appeared 3 times in the event log. Let's check, by the way. Yeah, so you see there are 3: register, select flight, register, select flight, register, select flight. Yeah, so we put 3 here. Hope I've answered your question. And also, for instance, book flight goes after select hotel only once, and here we can see 1 near this arrow. The next question: can we take session, pause day, or their combination as case ID? Are there any ways to decide what to take as the case? Oh, thank you very much. That is a great question. Yes, we can do that. And I think that, so maybe that is somehow related to what we discussed with Rostislav. Yes, indeed. So if we're monitoring some social networks, that's what I would do. I would consider maybe all these things all together to identify case ID. But what I would do next, I will try to understand what are the models I discover after that, the quality of these models. So it's empirical approach here. Try this, see what you get. Maybe some of these attributes, session or day, are not necessary. Maybe we can remove them. And yeah, so that is a very good question. Thank you very much. So I would be happy to answer more questions if we have any, and I can proceed to the second part of my slides. Okay, so that was about discovery, and as you can see, there are different models that we can discover. We can discover this process map that is very plain, very simple, but it is used in industry, in retail, in banking sectors. It's used everywhere. However, if we, for instance, deal with more complicated, sophisticated systems, if we want to model parallel behavior, we have to stick to Petrinet, for instance, or any other model. So, of course, also much depends on the model we select. So now let us move to the second part that is about conformance checking. So suppose we have an event log and we have a model and we want to compare the log against the model. So what this can be, for instance, we have discovered the model and we say, okay, this is a model of the behavior of our system. This is how our system organized. And then we want to check, and we have, for instance, event logs of unit tests. And we want to check if we cover our system's behavior with this event logs. And we want to relate event logs and process model. Or we have a process models in advance, and this is maybe not discovered model. Maybe this is a reference model, and this is how we think the system works. But it may work differently, and also for this we need conformance checking to find these deviations where we deviate from the behavior in a model. And there are different ways to do this. There is an algorithm that is known as an alignment that tries to find synchronous steps between the log and the model. So here you can see a table where we have log moves and we have model moves. The first row corresponds to the log. So we first register, then we book the flight, we book the hotel, and then suddenly we cancel our process. So that was not something that was not expected, and it is not even presented in our model. So if we will consider this simple model, for instance, there is no cancel event. So here I register, then we have two branches that go in parallel. We have book flight, we book hotel. This can be, by the way, they can be skipped. So here, these diamonds, they correspond to diamonds in simple flowchart diagrams. So here's just a choice. So either I do book hotel or I skip this event. And here we have a gateway that corresponds to parallel execution. So we do register, then we run two parallel branches. We can skip book, we can make book flight or skip it, the same for the hotel, and then here we have synchronization of these two parallel branches, and finally we pay. So here there is no cancel event, while this cancel event, for instance, can appear in event log. And what should we do? We should relate an event log in the process model and to find this deviation. So the first row corresponds to the log moves, to the log activity.
I wonder if it's only my problems with video.
I'm very sorry, I was disconnected.
Okay, you are back. Welcome back. So great.
Sorry?
Welcome back. We are happy to see you again.
Thank you so much.
We
Hope you
missed
can hear me.
approximately 1 minute. So you can just continue.
Sorry for
Thank
that.
you.
I got a message that I'm disconnected, and now I'm connected back. Thank you very much. So the first row corresponds to the event log. The second row corresponds to the model. And here we can relate the log and the model. So we're trying to replay the log. Here is our model. So the first thing we do, we make register together. We make a synchronous move in log, in a model. In the log we make register, in the model we make register. And we move, and now we have to execute two gateways, gateway 1 and gateway 2 for the model. They are silent, these are not activities, this is just routing elements, but the log is not moved. This sign, means that nothing is changed for the lock. This is just a skip, a sign, and we make it twice. And while we are doing nothing in the event log, in the model we're also doing almost nothing. We're just moving tokens in this net, but there are no activities here. Then we make a synchronous move. We make book flight in the log and we make book flight in the model. Then we make, for instance, we can make this step G4 in the model and nothing in the log. And now we can synchronize on the book hotel activity and so on. And finally, we will be in such a situation, in such a state, when we see something in the event log and there is nothing here in the model that corresponds to this cancel event. So we were moving synchronously in log in the model, and then finally we reach a state where we make a log move and we can't make nothing we can do here in model. And we can highlight the states in model and say, oh, here is a problem here. We have only log move that is not synchronous. So we have some unexpected event in our event log. And similarly, then when we proceed with the model, we finally reach the pay activity that is not represented in the event log. And this is model only move, sorry. So it's also not synchronous. That means that, okay, in our model something happened, something should have happened, but we can't see it in the event log. That's a problem. So this is another error, another deviation from the expected behavior. So this is one way we can do conformance checking. The other way, I'm sorry, I'm moving to this slide. So that was log against model. There are other ways how we can make conformance checking. We can compare two graphs. We can find two graph distances. If we represent our behavior as models, I do not say that these models are necessarily discovered from the event logs or constructed manually. We can, for instance, one model we can construct manually and say, okay, this is our perfect reference model and this is how it's supposed to be. And another model can be discovered from event log, and this is how it actually, how the system actually works. And now we want to find the differences between these two graphs, and here we can apply so-called approach, so-called minimal graph added distance. So this is the minimal number of operations we have to perform to transform one graph to another. So if we have one graph, the first you can see at top of the slide. So we have to remove two errors around the pay activity, and we have to add the construction in green that connects pay activity to other parts of the graph. So this is an example, and the benefit of this example is it very informative. It's visual because here we can see, okay, here are the differences of these two models, and this is the same example. So here we have an additional cancel event that was not represented in the initial our initial model. This approach can be also, of course, applied to real-life event logs, and we had an experience of analyzing the real-life event logs. So here we can see two process models that correspond to government services, and this is how users fill the forms. And it's interesting for these logs that we analyzed. I'm sorry, I think some noises. Sorry for the noises. So the first model at the top of the slide is a reference model. This is the model how it is supposed to be. And if you will have a look at the end of this model, there is a confirm event there that is highlighted in red. That means that it is not represented in the second model, in the model discovered. So in our reference model, we expect that the users will confirm the last step of this application. So as far as you can see, it's passport renewal process. So using some kind of government services online, you can apply for a new international passport, and it's expected that at the end you click confirm. But if we will analyze some, we just took some random traces and we constructed a model, and we saw that there is a loop between the activities, that users, they fill the form, they open it again, they save it, open again, and so on. But there was no confirm. I think that maybe that was the case because the event log was not complete, and it didn't contain traces we expected with the confirm event. However, according to the reference model, it was not expected that users will save the form, close the form, open the form, and so on, and we'll do it many times in a loop. So this is how conformance checking can be applied if we talk about graphs. And there is an open source tool that was developed, so you can also try this tool, that explicitly finds the differences between process models in graphs, and it relates the behaviors. There is one more conformance checking approach that I would like to talk about. So this is a joint work, and I was involved in this work here. Also, similarly, we have a model and we have an event log, and we want to make model to log comparison here. So let us consider the model. Again, this diamonds corresponds to choice. So what does it mean here? What does it mean? The model can replay two traces, A, B, C, D, E, or A, B, C, D, F. So here are these two traces. And suppose we have some kind of an event log that contains three traces, A, B, D, A, B, C, D, F. And we want to relay the log in the model. So actually, we can consider two parameters. Precision. So this parameter shows if the model is precise enough, if it doesn't allow too much behavior that is not represented in event log. So how can we do that? We can calculate the number of the same traces, and then we can divide it by the number of model traces. So the same trace, so we have only one trace that is the same, A, B, C, D, F. It is in the model and in the log. So that means that it is 1 divided by the number of traces in the model by 2. So that means that precision of the model is 0.5. That means, okay, only half of the model behavior is represented in the event log, and the model is too general, is not precise. It also allows us to do more. And another, the opposite, is recall. Again, we take the intersection of two sets, and now we divide it by the number of traces in the log. What does it mean? So recall is even simpler. That means if our model can replay all the traces from the event log. So we hope that our event log can be totally replayed by the model. Then recall is 1. But if nothing can be replayed, then recall is 0. And here again, we have intersection. Intersection is 1. So only 1 of 3 traces of this event log L can be replayed in the model. That is why we have 0.3 value here. Only 1 of 3 traces can be replayed. So this is how we relate to the log and the model. And this approach seems to be feasible. Why not? The only problem is that model may contain loops. And here you can see a loop. In this model, C can be executed as many times as we want. We can, here we execute C many times. And how can we calculate traces in this case? And in this case, a notion of so-called topological entropy is used. So this approach was proposed by Adam Poliviani. And my task was, I proposed also and was involved in the extensions of this approach that can also show us, for instance, how is good our test coverability. So if we have some model of our system, of our software system, and we see how it works, and we have some event logs from our tests, and we want to check if the coverage is good enough, then we can apply this approach even if we have cycles and have loops in our program. So it still works, but it is based on the notion of so-called topological entropy. So we still can assess the number of traces, and we still get here numbers between 0 and 1 that show us similarities, that measure and quantify similarities between logs and models. But we can deal with a more general and more complicated behavior. This was, so you can test this. It is available online and it is open source. So event log is represented usually as a XCS file, and process model as a Petrinet. And this is a very simple command line tool that you can run, and you can get these values from 0 to 1 to assess, for instance, the coverage of your tests, or just to relate some process model to an event log, or even compared to event logs, or even compared to process models, because at the end, internally we represent them as finite state machines. So that was all about the conformance checking, and I'm really looking forward to answer your questions.
Okay, thank you, Anna, again. I have two questions. The first one is probably more philosophical. Is it important for a model to be human readable?
Oh, great. Thank you very much. I think it's a great question. I think yes and no. Let me explain. Sometimes we only need, that depends on what we need from our model. If we need some just behavior, and we do not care how this behavior is represented, we only care that it's exact, that it's correct. And we may have model of thousands of nodes and arcs, but actually we are okay with this, because the only thing we need is is just this behavior that is formally represented by this model. And but of course, at the same time, this can be important if we want to get the model as a final result, if we want to print it out and hang on the wall and say, okay, this is my model, I like it so much, and it's super simple, and I totally understand what is happening there in the process. Yes. So yeah, thank you very much. Great questions, and there are two answers. There is one more
another
question.
Question is more about the. Yes, can you hear me? Yes. So in all your examples, the system was specific for a user, like one person just registers for a flight, whatever. But what if you are working with system with joint state? For example, task tracking system. Consider, for example, one person just logs into the system and submits a bug. Then another person sees this bug and changes its priority or severity to something different. Then developer looks into the bugs and introduces some changes again. It's fixed or it's not reproducible, etc., etc. So can we work with systems like that? Thank you.
Great, thank you very much for this question. Again, I think this again brings us back to what case ID is, and I think that case ID in this case is a bug ID. And all these users are just additional attributes and resources in the system.
Okay, I see. Great, thank you.
Okay, one more question.
We still have 5 minutes for questions. I wonder if anyone else.
Yes, there are more questions. Petrinet is represented, in which format Petrinet is represented, and Okay, and the second question already contains and answers the first question. So yes, Petrinet usually represented in PNML format, which is XML. It's just an extension of XML format. What program would I recommend? I would recommend it's a rather old program, but actually it works. It is called Jasper. Can I type it in chat like this? Can you see this? Maybe I can also. No, I can't send in chat. Sorry for that. So the program is called Jasper. It's a pretty old, but it works. Also, there is a tool that is called Prom. But Prom you can't model Petrinets there. And by the way, Jasper, thank you very much. Great question. Yeah, I gave it a thought and I understood there are many more tools. If you will just search online where I can model Petrinets, you will see a lot of tools that are usually open source or usually they are free, where you can draw. And there is at the Petrinets there is an additional section where researchers present their open source tools. So there are a lot of them. Some are more powerful, some are less, but there are many. And of course, when you choose this tool, you have to keep an eye on what on the formats. If you're interested in PNML because you want to integrate this tool, for instance, with Entropia, yeah, so you have to check that it will be able to export diagrams in PNML format. So I'm happy to answer your questions if you have more questions.
In fact, we are perfectly timed, exactly 1 hour. So I suggest probably to stop here, and I assume you'll have you'll continue next time, because today we had only just basic introduction, and I hope to see some more probably concrete applications to very specific examples and probably some tools with more deeper dive in. So thank you again, and thank you everyone for joining our seminar.
Thank you very much. Thank you very much for having me here. It was my pleasure to present to make this presentation. And I'm very sorry for the beginning of the lecture because I heard myself from from a computer and there was an interruption at the beginning. Yeah, but I hope that at the end everything was okay. So thank you very much.